I gave a speech recently on the occasion of the 550th anniversary of the University of Basel, which opened its doors 20 years after Gutenberg made his invention, not too far away from where he invented the printing press. And I said, wow, that's exciting. You must have had some of his books when you opened your doors. And they said, yes, we got them very quickly. It was only a century later. That is how technology evolved and spread half a millennium ago. It took actually 400 years for the printing press to reach a mass audience. We did better in the 20th century. The telephone only took 50 years to reach a quarter of the American and English and European populations. The later 20th century was faster yet. The cell phone reached a quarter of the population in 7 years. Social networks, wikis, and blogs did that in 3 years. The pace of change is continually getting faster and faster. I've studied this. It's on a very continual progression of change. Just think about how different things are than 3 years ago. 3 or 4 years ago, people didn't use social networks. The world has changed dramatically, and it's not going to stop. In fact, it's going to continue to accelerate. And so lifelong learning is a topic that's very important to me. I actually co-founded a university. This is the insignia of it, Singularity University. It's backed by Google. We have a permanent campus that the American Space Agency, NASA, gave us. We have about 60 faculty. Last class was 80 students, picked out of 2,000 applicants. And the goal is actually to study these exponentially growing information technologies that are causing this acceleration, and to actually do team projects to address major world problems like availability of water and housing, food, poverty, using these exponentially growing technologies, deal with their downside, because technology is a double-edged sword. And it is our view that people need to keep learning for a lifetime. The model where you learned a trade or a profession in school, and then you practice that for 40 years, if that, until you retired, is no longer applicable at all. Particularly in your companies, I'm sure people change what they're actually doing every year. A year is a long time. It's something like telecommunications, the whole landscape changes. And I'd like to talk to you about what's driving this, which is the exponential growth of information technology. Information technology builds on itself. We always use the latest computers to create the next generation of computers, which is why it grows in an exponential manner. And I have a whole theoretical examination, mathematical treatment of why this is the case. But the strongest evidence for it is the empirical case, and I'll share that with you. It's remarkable how smooth and predictable these trends have been. It's common wisdom that you can't predict the future. And that's true of specific projects. There were 30 companies vying to be the next search engine over a dozen years ago. The fact that it'd be these couple of kids at Stanford with their late-night dorm room project, that they would take over the world of search, that was hard to predict. But the fact that search was becoming feasible and that the enabling factors of sufficient price performance of computation and communication were coming into place to make that viable, that you could predict. And it's amazing how predictable these phenomena are. I decided I would be an inventor when I was 5. Those first inventions didn't work out that well. I discovered the computer at 12. Not so remarkable for a 12-year-old to use a computer today. In fact, it's pretty remarkable if they don't. Back in 1960, when I was 12, there were only 12 computers in all of New York City, so it was a little more unusual. I quickly realized that the key to being successful as an inventor, and I'm sure this is true of all of your companies as well, is timing. Larry Page and Sergey Brin had a great idea there in reversing the links on the internet to create a better search engine, but they did it at exactly the right time. If they were a little earlier, a little later, we wouldn't be aware of Google today. So, being an engineer, I gathered a lot of data. My expectation was you can't predict the future. I didn't expect to find anything very predictable. And I made a rather startling discovery. If you measure the underlying properties of information technology, like the power of computers per dollar, instructions per second per dollar. That measures how much computation you get per dollar or per pound or per euro. It forms a remarkably smooth exponential trajectory, and I'll show you that, that's been unperturbed and very smooth and predictable since the 1890 American census, when we first used automated data processing equipment. And it went through thick and thin, through war and peace, through boom times and recessions. It went through the Great Depression. People said, well, that must have slowed it down. No, it had no impact on it. How about the recent worldwide recession? That must have slowed it down a little. No, not at all. Well, what about war? That must have accelerated. War is the father of invention. No, that didn't happen either. World War I, World War II, the Cold War had no impact on it. It's just this very smooth curve on a logarithmic graph. I'll show it to you. I had that in 1981 with the data through 1980, projected it out through 2050. We're now at 2012, and it's very much on that trajectory very precisely. You might wonder, well, how could that be? Because what is it that we're measuring? We're actually measuring invention and creativity and entrepreneurship and competition. That must be very unpredictable. Indeed, individual projects are very unpredictable, but the overall impact of many different people doing these activities is predictable. We see similar results in other areas of science. For example, thermodynamics, which comes from the 19th century, predicts the future of a gas. And if you look at the mathematics of thermodynamics, it actually models each particle as following a random walk. So by definition, I can't tell where this molecule will be 10 seconds from now. It's random. Yet the overall properties of the gas, made up of a large number of these random, unpredictable particles, is very predictable to a high degree of precision according to the laws. We consider them basic scientific laws of thermodynamics, which is basically a statistical result of the laws of large numbers. If there were only 3 or 4 people working on computers or other aspects of information technologies, communication technologies, biological technologies, now that health and medicine is an information technology, it would be unpredictable and random. But we don't have 3 or 4 people. We have hundreds of thousands, if not millions of people contributing to some aspect of it. So the overall result is remarkably predictable when we can find these underlying properties. And I'll show you a few dozen examples of this. I have a team of 10 people that helps me gather this data, and we have hundreds of graphs like this. It really belies the common wisdom that you can't predict the future. And there's 2 other important points about it. One is that it's not intuitive. We have an intuition about the future. In fact, that's why we have brains. If you ask, well, why did evolution come up with brains? It is to predict the future. So when we all walked through the savannah 1,000 years ago, we saw, oh, there's an animal going this way, and I'm going that way. We're going to meet up there. We made linear predictions in our neocortex on the progression of our own path and of an animal, and that worked very well for survival. Okay, we're going to meet up there. I'm not going to go that way. I'm going to go this way. It helped us survive. That's why we have brains. But these built-in predictors of the future are linear, not exponential. It works well for taking a sojourn in the savannah 1,000 years ago. It doesn't work well for predicting the future of information technology, yet that is our intuition. The very common debate I have with critics is they're looking at the current state of affairs, making linear predictions about where we will go, and saying, well, it's just not credible that the technology will be 1,000,000 times more powerful in 20 years. But that's in fact what's happened. I saw the ARPANET, created by the Advanced Research Projects Agency of the American Department of Defense, doubling every year in the early 80s. I did the math and said, wow, this is going to be a World Wide Web connecting hundreds of millions of people to each other and to vast knowledge resources emerging in the mid to late 1990s. People thought that was nuts when the entire American defense budget could only tie together 2,000 scientists. But that's the power of exponential growth. That is what happened. I saw the chess computers doubling in power every year, did the math, and said, okay, this is going to make them powerful enough to defeat the world chess champion. In 1998, is what I said. I said that in the early 80s. People thought that was ridiculous when an average player could beat the best computers, but that is what happened. It happened in 97. Also predicted that when that happened, we would immediately dismiss chess of being of any significance. And indeed, that happened as well. As soon as Deep Blue defeated Kasparov, people saying, well, it was to be expected. Chess is just a logic game, and these are logic machines. And of course, a computer would defeat a human. They will never be able to match human performance in areas like language and the subtlety of metaphors and jokes and puns. That's why the recent defeat of the world's best Jeopardy players, how many people heard of the IBM computer that defeated the best Jeopardy players? That's why that was so significant, because Jeopardy, if you're familiar with it, is a language game that deals with metaphors and puns and so on. I'll come back to the significance of Watson. But exponential growth is not intuitive, and that's why it seems surprising. The actual rate of exponential growth is increasing. We doubled the power of computers per unit currency every 3 years in 1900, every 2 years in 1950. It was 12 months in the year 2000. It's now down to 11 months. Even just straight exponential growth is quite surprising, because our intuition is linear. So if I take 30 steps linearly, 1, 2, 3, 4, at step 30, I'm at 30. If I take 30 steps exponentially, that reflects the reality of information technology, 2, 4, 8, 16. At step 30, I'm at 1 billion. And that's not an idle speculation about the future. This computer, which I carry around, and maybe you have a similar one, is actually several billion times more powerful per unit currency, constant unit currency, than the computer I used when I was a student. It is 1 million times cheaper. It's several thousand times more powerful. It's also 100,000 times smaller. We're shrinking technology. It's another exponential rate of factor of 100 in 3D volume per decade. This will be the size of a blood cell in 25 years. It will again be 1 billion times more powerful in terms of price performance of both computation and communication. Gives you some idea of what will be feasible. As price performance reaches different levels, whole new applications become feasible. It's not just because Mark Zuckerberg had this sort of cool idea of a better way to meet girls in 2004 that we have Facebook. This just wasn't cost effective in the year 2000. And search engines were not cost effective in 1990. So when the price performance reaches certain points, whole new applications explode on the landscape. You can actually predict when that will be by looking at these very predictable curves, and I'll show you more about that. The other point I want to make is that it's not just these gadgets we carry around in this sort of weird world of information technology as we commonly know it. Information technology is increasingly affecting more and more fields. Take, for example, health and medicine. That was not an information technology just a few years ago. We didn't have the genome, which is basically the object code of biology, until 2003. By the way, that was also an exponential progression. That project, the Human Genome Project, was announced in 1990. Mainstream scientists were skeptical, saying, there's no way you're going to collect the whole human genome in 15 years. We had our best PhD students and most advanced equipment around the world. We collected 1/10,000th of the genome in 1989. This is going to take centuries. Halfway through the project, chronologically, 7.5 years into this 15-year project, 1% of the project had been completed. So the skeptics were saying, see, I told you this wasn't going to work. Here, it's about 7 years, 1% of the project is going to take 700 years, just like we said. My reaction was, no, we're almost done. 1%, once you reach 1% on an exponential trajectory, you're almost finished. That's only 7 doublings from 100%. And indeed, it continued to double every year and was done 7 years later. And that's continued past the completion of the project in 2003. And every other aspect of biology, turning genes into proteins and how proteins interact with three-dimensional forces in vivo, and being able to simulate regions of the brain, scan brain interconnections, the Connectome project. All of these projects are scaling up at an exponential pace. And health and medicine is becoming an information technology. The cutting edge of it now, the research phase, is now an information technology where we actually are understanding the processes that lead to HIV infection or cancer and are being able to reprogram it. By either changing genes, we can turn genes off with RNA interference, we can add new genes with forms of gene therapy. I'm involved with a project where we take cells out of the body, add a new gene in vitro, inspect it, multiply it a millionfold, inject it back in the body. In the case of this project, they're lung cells, so now you have 1 million new lung cells going through your bloodstream. They end up back in the lungs. The body recognizes them as lung cells that have your DNA, but with a new gene added. That gene happens to be the gene, the absence of which causes a fatal disease, pulmonary hypertension. And this has actually cured that disease by adding that gene back in, and it's undergoing human trials. It's just one of hundreds of examples of that process. Stem cell therapies, if you have a heart attack, half of heart attack survivors have a damaged heart. It's called heart failure. They have a low, what's called ejection fraction, and they can be cripples. They can hardly walk. My father had this condition in the 1960s and died in 1970 of it. You can now get stem cell treatments that will actually rejuvenate the heart with stem cells with your own DNA. And I know people who could hardly walk and now have been fully rejuvenated. And there are hundreds of examples like that. We could talk all afternoon about it. The key point is that health and medicine, which used to be just hit or miss, we just sort of find things, or here's something that lowers blood pressure, we don't really know why it works, to a process where we actually understand the information processes. Our understanding is growing exponentially. The power of the tools to reprogram it is also growing exponentially. The things I just mentioned are in an early stage, but they're actually already reaching clinical practice. They will be 1,000 times more powerful than today in 10 years, 1 million times more powerful in 20 years. That's the implication of doubling in power every year. How about physical things? Just like a house or a plane or a violin. Take a physical thing like a book or a movie or a music album. If I wanted to send you one of those a few years ago, I would send you a postal package. Today, I can send you an email attachment, and you can turn it into a book or a sound recording or a movie. I can actually send you a violin today as an email attachment if you happen to have a three-dimensional printer. Another one of these emerging technologies. I'll show you the cover of The Economist magazine from a year ago that has a picture of a violin that plays quite well, and professional violinists like it. It was printed out on a three-dimensional printer. We have a project at Singularity University where we're printing out a house, not at one time, but in modules that you snap together Lego style to create very inexpensive, high-quality housing for the developing world. Somebody printed out an airplane that way, snapped it together, and flew in it. The world of physical things is also turning into information. Right now, the scale of precision of these three-dimensional printers is in microns, millionths of a meter. It's pretty good for certain things like violins. It's not good enough for something like clothing. The scale of precision, though, is improving at a rate of 100 in 3D volume per decade. This will be full nanotechnology in the 2020s. We'll be able to print out almost all the physical things we need from very low-cost input materials and a three-dimensional printer. Today, and the cost of these three-dimensional printers is coming down. Remember how paper printers came down. I remember when I sold my first company, which is now Nuance, which created Siri for those of you who talk to your iPhones, to Xerox, and they were giving me a tour of the advanced technologies that Xerox had, and they brought me into this room and they said, "This is the future of printing." And they brought me into this room, and this big machine cost millions of dollars. It was a laser printer. And today you can buy them for $79. Three-dimensional printers are doing the same thing. They started at tens of thousands, and now mid-thousands, $5,000 or $6,000. That's still not ready for mainstream use. They will be in hundreds of dollars within a few years. If you bought a three-dimensional printer today, you could print out 70% of the parts you need to print out another three-dimensional printer. That will be 100% within 5 or 10 years. So we can send one three-dimensional printer to Nigeria, and they can print out another one, and the two can print out 4, and pretty soon they can have a three-dimensional printer for every person or family and print out the physical things you need. That is going to revolutionize manufacturing. It's a little bit before the storm, but you can see it coming if you look at these very predictable trends. So let me show you just how predictable this is. And I'll show you a few dozen examples. As I mentioned, we have hundreds of these. But just to give you an idea of how predictable this is, this is what I wanted to cover. Any questions on any of this? All right, I'll go through it a little more slowly. So I covered a lot of this. I'll skip over some slides. But here is Cooper's law, and over here, you may be familiar with an invention of Martin Cooper. It's called the mobile phone. And he has studied communication, wireless transmission. And one word about the nature of these graphs, they're logarithmic graphs. So as we go up the graph, we're not adding to something, we're actually multiplying by powers of 10. So every level on these graphs, on this graph, is 1,000 times greater than the level below it. A straight line on a logarithmic scale represents exponential growth. And so this actually represents trillions-fold increase in something because every level is 1,000. And so what is it that we're measuring here? It's number of bits we transmit wirelessly in the world. 100 years ago, that was Morse code over AM radio. Today, it's 4G networks. But look at how predictable and smooth a trajectory that is. You would think it would be very varied, that maybe there'd be a blip in World War II because there was more communication. It's just remarkable how smooth these trajectories are. I'll show you the first one that I did, which was this one. So I only had it through 1980, because I collected it in 1981. It was really the first graph I looked at. And I was really quite surprised at how smooth a trajectory that is. Even through 1980, that represents trillions-fold increase, in this case in the power of computation per constant dollar. Instructions per second per dollar. Every level on this graph is 100,000 times greater than the level below it. And one of the criticisms I get is, Kurzweil takes these exponentials and projects them out indefinitely. We all know exponential growth can't go on forever. You have 2 rabbits in Australia, you get 4 rabbits, 8 rabbits, 16 rabbits, but finally when they eat up all the foliage, that exponential growth comes crashing to a halt. Isn't that the case here also? The answer, it is the case for specific paradigms. What happens in information technology is it creates research pressure to create the next paradigm. And so the next paradigm is ready when we need it to be. People say, oh, this Moore's law. Well, Moore's law is just this part here, having to do with chips. This exponential growth started decades before Gordon Moore was even born. 1950s, vacuum tubes. We built computers from vacuum tubes. CBS, the American network, predicted the election of Eisenhower, the first time the networks did that with a computer based on vacuum tubes. And every year they were making the vacuum tube smaller and smaller, and finally that hit a wall. They couldn't make the vacuum tube smaller and keep the vacuum, and that was the end of the shrinking of vacuum tubes. It was not the end of the exponential growth of computing. It just went to another method, to transistors, and finally to chips. People are predicting the end of Moore's law. Gordon Moore originally said 2002. Intel now says 2022. By that time, the key features on a transistor will be 4 nanometers, and we won't be able to shrink chips anymore. But we'll then go to the 6th paradigm, which if you speak to Justin Ratner, the Chief Technology Officer of Intel, will tell you they already have working, which is 3-dimensional computing. Not chips, they're really more like cubes. And that will keep this exponential growth going well into the 21st century. In fact, into the late 21st century. But the most remarkable thing about this, aside from the fact that it's trillions-fold increase, several billion-fold just since I was a student, is look at how smooth a trajectory that is. There was no impact of World War I, World War II, the Cold War, the Great Depression, and so on. And I won't dwell on these examples of electronics. There's the cost of a transistor, exponential graph, trillions-fold improvement. You could buy a transistor for $1 in 1968. You can buy several billion now. And they're actually better because they're faster, because electrons have less distance to travel. The cost of a transistor cycle has come down by half every year. That's basically equivalent to a 50% deflation rate in information technology. So you can buy an iPhone today that's twice as good for half the price as compared to 2 years ago. That's a fourfold increase in price performance. And it's not just because Apple is so clever. That's true of information technology in general. And you say, okay, it's true of this sort of weird world of these little gadgets and electronics and communications, but my point is it's increasingly going to encompass everything we care about. Economists actually worry about deflation. The concern, particularly with information technology, if I can get the same stuff, and if you think about three-dimensional printing, we're actually talking about stuff, a year later for half the cost, okay, I will buy more, that's an economic rule, but I'm not going to double my consumption. There's a limit to how much I can consume. So the size of the economy, as it pertains to these information technologies, and that will be most of the economy by the 2020s, is going to shrink. Maybe not as measured in bits or base pairs, but as measured in constant dollars or pounds. And for a variety of actually good reasons, that would not be a good thing. But that's actually not what we see. We actually more than double our consumption. There's actually been 18% growth in constant currency every year for the last 50 years in every form of information technology, despite the fact you can get twice as much of it each year for the same price. And the reason for that I alluded to earlier. As price performance reaches certain points, whole new applications explode. We wouldn't be having widespread dissemination of videos over the internet if the costs were still what they were 10 years ago. The National Institutes of Health in the United States wouldn't be collecting 1 million genomes to do a grand study relating disease states to genetic states if they still cost $1 billion each, which is what the first one cost. So this slope on this logarithmic graph is a doubling every year the amount of genetic data you sequence. The cost has come down by half every year from $10 in 1990 to a small fraction of a penny today. Every other aspect of biology, the Proteome Project, as we're understanding how the genes express themselves in proteins and the proteins interact with each other, the Connectome Project, are all scaling up in a similar exponential manner. And this is now beginning to reach clinical practice. I mentioned heart rejuvenation from heart attacks. Every single organ of the body is being, is at least experimentally being rejuvenated or being regrown using these types of therapies. Communication technology is very democratizing. I mentioned the example of the Soviet Union. We can see examples with social networks today. It's democratizing on more than just a political level. A woman walks into her doctor's office. She's armed with knowledge of her disease that's very sophisticated from all the thousands or hundreds of thousands of people that have that condition worldwide. And she may know more about the disease than the doctor. There's even collaborative decision-making now to actually solve the problem. So you have 100,000 people with a disease. They have the skills to solve that problem, and they certainly have the motivation, and that is happening. There's many different types of problems. For example, mathematical problems that have been unsolved for centuries, which were solved through this type of collaborative decision-making among hundreds or thousands of mathematicians that would have been impossible otherwise. This is the graph I had in the 1980s. I had just a few points on it, projected it out, saw this World Wide Web emerging 15 years later in the late 90s. This is the same data on a linear scale, and that is how we experience the world. So the casual observer, it looked like the World Wide Web came out of nowhere. but you could see it coming if you looked at the exponential trajectory. Here's that violin on the cover of your fine magazine, which I'm an avid reader of. And that's not an artist's conception. And there's increasingly wide variety of materials at a pretty fine resolution in microns that you can print out today. But this technology is going to get less expensive and more capable with finer and finer features. If you go out to the 2020s, we really will be able to print out the physical things we need at extremely low cost. And you know, this factor is factored out of economic statistics. So when we talk if today you produce or consume $1 of computation or communication or biological technologies, it counts for $1 or £1 of economic activity, despite the fact that it constitutes $1 million of these activities, or this computation or communication or other information technologies, circa 1990, $1 billion circa 1975. But we still count it as $1. 1 hour of human labor still counts for an hour of human labor. We expect people to do more. I know, because I've been managing work groups for 45 years, and I can have groups now of a few people who can accomplish in weeks what used to take groups of 100 people years. We are more productive, but all of that is actually factored out of the economic statistics because we ignore the fact that $1 buys so much more, twice as much as just last year, in information technology. And increasingly that's going to encompass, as I said, everything we care about. One of the applications of nanotechnology will be blood cell-sized devices that can perform therapeutic functions in the body. If that sounds very futuristic, I point out there's already dozens of animal experiments of doing exactly that. One scientist actually cured type 1 diabetes in rats with a blood cell-sized device, nano-engineered, 7 nanometer pores, lets insulin out in a controlled fashion, blocks antibodies, and they're actually gearing up for human trials with a human version of it. The quintessential application would be a robotic white blood cell, which would basically be an augmentation of our immune system. Our biological white blood cells are pretty good. I've actually watched one of mine in a microscope outside my body, and it actually detected a bacteria and surrounded it. It was actually quite clever. It's an intelligent cell, and it destroyed it. It was pretty boring to watch. It took 2 hours to do that. And there are well-known limitations. Our white blood cells don't recognize cancer. It thinks it's you, so it doesn't attack cancer. Sometimes it thinks you are the enemy, and that's the nature of autoimmune disorders. We can create a much more intelligent robotic white blood cell that would be much more powerful, faster, that could download new software from the internet for new pathogens and so on. I used to call this a killer app, but that was such a good idea for a health technology. But that's coming in the 2020s. So Time magazine in the United States did a cover story on my law of accelerating returns. And they wanted to print my computer graph. They said, we want you to put this particular computer on it that we actually talked about in our magazine a few weeks ago. And I said, well, okay, it's not going to be above the curve, because I've never seen a computer above the curve. Could be below the curve, because sometimes you have computers that are not cost effective. Maybe they come with nice furniture or something. But it was actually right on the curve. It's the last dot there. This is a curve I laid out in 1980. And as the new computers come along, they fit right on the curve. It's really quite remarkable how predictive it has been. This reverse engineering the human brain is something I've been interested in for about 50 years. And I'm writing a book on it now called How the Mind Works and How to Build One. Every aspect of this is scaling up exponentially. The spatial resolution of brain scanning is doubling every year, both non-invasive and invasive. The amount of data we're gathering is doubling. We're showing that we can turn this data into working models and simulations of brain regions. This is a small slice of the cerebral cortex, neocortex, that has actually been simulated. And I was on a panel recently with the head of the Blue Brain Project, which is seeking to simulate the entire neocortex, and I was actually the conservative on the panel because Henry Markram, the head of the project, said, "Oh, we'll simulate the whole brain by 2018. I said, well, you may have something running by 2018, but you're not going to be able to show that it works, because part of the paradigm of human intelligence is education, which is what we're interested in here at this conference. You have to, even if you got a perfect simulation of the neocortex, it's not going to know anything, just like the neocortex in the human. You're going to have to educate it. And we don't have to take 20 years to do that. We can accelerate that. Watson actually educated itself by reading Wikipedia and other encyclopedias, and it didn't, you and I could read Wikipedia. It would take actually 2 years, I figured, because by that time it will have doubled in size. But it can do that in a matter of weeks, but we still have to devise methods of doing that. Then you're going to have to improve the design. My date has been 2029 by the time we can actually achieve human-level intelligence through this type of work. Nonetheless, it is progressing at an exponential pace in many different aspects. And we are simulating different regions of the brain, different parts of the cerebral cortex, the visual cortex, the auditory cortex, cerebellum, which actually comprises half the neurons in the brain. It's where we do our skill formation, like catching a fly ball. We always wondered, how does a 10-year-old kid do that? I mean, she sees the ball going up and she moves her hand and then maybe catches the ball. In order to accomplish that, she needs to solve a dozen simultaneous differential equations in 1 or 2 seconds. And most 10-year-olds haven't taken calculus. So how does that work? The cerebellum actually does solve those equations. That's part of our understanding of how it works. And this has been reverse engineered and modeled and simulated and tested on skill formation tasks where it performs comparably to human skill formation. So we are making rapid progress on all of this. Let me switch gears and talk about whether or not this is a good thing. There's a pretty popular intellectual movement that says the world's getting worse. And part of that orientation is to say that technology is responsible. The world was much better off before it was spoiled by technology. I invite those people to read Thomas Hobbes, who describes life a couple hundred years ago as short, brutish, disaster-prone, disease-filled, poverty-filled, or Charles Dickens, or any one of a number of writers who have really brought those times to life. One of the reasons we think things are getting worse is we are doing a much better job of understanding what's wrong with the world. When there's a battle in Fallujah, we used to say it's in our living rooms, now it's literally in our palm tops. We are there, we experience it. If 30,000 people died in a battle in World War II, unless you were in the battle, which England was, the United States was a little bit removed, you didn't see it until maybe a few weeks later as a grainy newsreel in the movie theaters. World War I, there was no videos. You didn't see it at all unless you experienced it directly. Maybe you read about it in the newspapers, but only a very small fraction of the population had access to newspapers. 19th century, there was just no information at all. So we have much better information about what's wrong with the world. People's algorithm for, are things getting better or worse, is how often do I hear about problems? And we hear about them more and more often. For one thing, people tend to gravitate to problems. They're more dramatic. It makes the news more interesting. But also, we are an empathetic civilization, an empathetic species. So we like to hear about problems and then seek to solve them. We can't always solve them right away, which leaves people frustrated. But let's take a broad perspective. I have actually several dozens of graphs like this, looking at different aspects of human well-being over the centuries. So this is 1800 on 2 parameters, wealth and health. So wealth is represented by income per person in dollars, today's dollars. So in today's dollars, the wealth was in hundreds of dollars. Each of these circles are countries. The big red circle is China. Watch China, actually, because it does some interesting things. On the x-axis, it's life expectancy on the linear scale. It was in the 20s and 30s in 1800. Worldwide average was 37. It's the beginning of the first industrial revolution. Few countries are experimenting and getting benefits. Most of the world has not heard of it yet. But as we reach the 20th century, there's a wind that carries all these nations towards the upper right-hand corner of the graph. The have-not divide remains, but at the end of the process, the countries that are worst off are far better off than the countries that were best off at the beginning of the process. And this wind is not stopping. In fact, it's going to go into high gear now that more and more aspects of life are benefiting from information technology. Also, keep in mind that this income per person is measured in constant dollars, ignoring the fact that a dollar buys so much more in terms of information technology, which ultimately will include physical things and so on. But the world is getting better, and the exponential growth of information technology is the driver. There's still a gap, and we are much more mindful of what that means because we have much better information about the world. Education, we are investing far more in education. It has been controversial for 200 years, since the beginning of the Industrial Revolution, as to what the impact of these technologies is on jobs. And jobs is always, people look at it from a very narrow political perspective of how does it compare to last year or 2 years ago. We really need to look at a broad perspective to see the overall impact. The Industrial Revolution started in this country, in the textile industry, and somebody looked at their friend who had a job spinning thread or weaving cloth, and suddenly they were replaced by one person with a machine that could do the work of 10 or 50 people. And the more and more of these machines for different aspects of the textile industry were coming out, and then it spread to other industries, including agriculture. People thought employment is a thing of the past, and or will be soon. What was hard to point out is there are new jobs coming, but I can't tell you what they are because I don't know what they are, and they're industries that don't exist yet, but they will. If I were prescient futures to 1900, I would say, okay, a third of you work on farms, a third of you work in factories as factory workers, and I predict in 100 years, in the year 2000, that's going to be 3% and 3%. And everyone would go, oh my God, we're going to be out of work. And I said, well, don't worry, you'll get jobs directing corporate learning for life, designing websites for education, designing new chip designs, and nobody would have any idea what I'm talking about. In fact, the majority of jobs in the world today did not exist 50 years ago, let alone 100 years ago. But you can't describe what these future jobs are. But that has been the reality consistently. In fact, we have a greater number of jobs. We eliminate jobs at the bottom of the skill ladder. We add new jobs at the top of the skill ladder. People say, well, okay, you're adding new jobs, but it must be very few compared to the ones that are being eliminated. It's not true. In the United States, we have 2/3 of the working age civilian population working at jobs. That was 1/3 100 years ago. We've gone from 12 million jobs to about 100 million jobs since 1870 in the United States. And the new jobs pay 10 times as much in constant dollars as the jobs that we've eliminated. And we are investing more in education, including lifelong education, to enable this skill ladder to go up. So in K through 12, we're spending 10 times as much per capita. This is true in England, it's true in the United States. In constant dollars compared to a century ago. In 1870, we had 50,000 college students in the United States. We have over 10 million today. And education is an increasingly important part of employment because we're constantly changing the nature of work. I mean, just look at the work in your industries and how different it is to utilize all the latest technology, and that requires constant training, and that's only going to accelerate. Another graph in terms of the progress we're making, this is number of years of schooling. There's a gap between the developed world on the top and the undeveloped world, but they're both moving in the right direction. We've tripled the amount of education the average child receives in the developing world, doubled it in the developed world. So these trends are moving in the right direction. I'll just mention one thing about resources. People say, well, that's great. We're going to extend longevity. That's going to make the environment even worse, and we're going to run out of energy and resources and water and food. And that's true if we stick with 19th century technologies to do those things. We're actually awash in energy. We have 10,000 times more sunlight than we need to meet 100% of our energy needs. But I can't plug my refrigerator into the sun, but we can turn sunlight into electricity. Nanotechnology, which is an information technology of understanding the properties of matter at a finer and finer scale, is enabling us to create more and more efficient solar panels. This is the cost per watt of solar energy coming down very rapidly. And this is the total amount of solar energy we're producing on a logarithmic scale. Every level on this graph is 10 times the level below it. This slope is a doubling every 2 years. Not for the last 2 years, but for the last 30 years. We've been doubling every 2 years the total amount of solar energy in the world. It's now between 7 and 8 doublings from 100%. So it's between 0.5% and 1% of the world's energy needs. And people tend to dismiss technology. Oh, it's a nice thing, but it's just a fringe player. It's less than 1% of what we need. Maybe it'll become 2% or 4%, but it's never going to be a significant player, ignoring the exponential growth. That's what we did with the Genome Project. That's what people did with the internet. They're doing that now with solar energy. But we are only 8 doublings at 2 years each from meeting 100% of our energy needs. I had this discussion recently with this was actually a study that Larry Page and I did for the National Academy of Engineering in the United States. It was adopted by the United States. I had a meeting recently with the Prime Minister of Israel, who actually used to be in my class at the MIT Sloan School. And he said, Ray, do we have enough sunlight to do that with, to double 8 more times? And I said, yes, we have 10,000 times more than we need. After we double 8 more times and are potentially meeting 100% of our energy needs, we'll be using 1 part in 10,000 of the sunlight. And there's a similar story with water. There are new decentralized water technologies that can clean up dirty water. We have plenty of water. It's just not drinkable, but we have the technologies that can clean it up. The Dean Kamen water machine, for example, can meet the water needs of 100 people. In high-volume production would be $1,000 each. We actually figured out you could meet the entire unmet water need of Africa for a few $billion, which is a fraction of the cost of a water dam that moves dirty water from one place to another. If we had more time, I could talk about new food technologies that have a similar story. We have plenty of resources, including housing, using these 3-dimensional printing technologies to meet the resource needs of an expanding population, which is not going to expand that quickly anyway. So I'll just show you one last trend, then we'll take some questions. This is the progress we made over the last 1,000 years. Life expectancy was about 20 to 23 1,000 years ago. I gave a speech recently to middle school students, 12 and 13-year-olds, and I told them, you all would be senior citizens if it hadn't been for this progress we've made. And looking at this group, I think you'd all be senior citizens if this was 1800 and life expectancy was 37. It's pushing 80 now, but that's not going to stay there. It is increasing, but it's going to really go into high gear as the fruits of the biotechnology revolution reach clinical practice. These technologies will be 1,000,000 times more powerful in 20 years, and it really will be a different era. We'll be adding at that time, according to our models, more than a year every year, not just to infant life expectancy, but to your remaining life expectancy. It's not a guarantee, but it's kind of a tipping point. So if you can hang in there, we may get to see the remarkable century ahead. Thank you very much.